All right, so we did a couple of lessons on word problems, max and min word problems, and now we're switching back over to what we sort of started with in the unit, and this will transition into the rest of this unit, which is going to be curve sketching. After this lesson, there's going to be 4 lessons on curve sketching, so that's a big part of the unit, obviously. And what this lesson is about is actually really very similar to the first lesson of this unit, which goes back to this idea of classifying critical points. And we had these 6 different ways that we classified critical points based on the derivative. So we look at the derivative, we look at whether it is positive or negative, and among other things, whether the derivative exists, whether the function exists at that location. And that allows us to classify these points as possibly something interesting happening or maybe not. And so, as I said, this is going to lead into curve sketching. So when we want to sketch a curve, this is going to help us know what's happening at these locations, what it looks like, that sort of thing. So we want to remember these different ways of classifying critical points. And the only difference that the lesson today really has compared to this first lesson from this unit is in this first lesson, it was in a given domain, and now we're going to do it on the entire domain of the function. So we're going to sort of assess the entire domain, look for all critical points, classify all critical points, and again, that's going to lead into curve sketching. So this first one, I would say when you're doing these, in particular, since, we're getting into curve sketching, you want to, the first thing you probably want to do is take a look at that function and decide what kind of a function it is. So is it a rational function, polynomial function? We will eventually get into trig and logarithmic functions. So this one's just polynomial, right? So there's lots of properties of polynomial functions that should start sort of that we should start to consider, but we're going to do the same process no matter what kind of function it is, and that is take the derivative, determine where the derivative is equal to 0 and where it does not exist. Again, now we're talking about the entire domain of the function. This is what I meant. The polynomial functions, the domain is always everywhere. We will get into rational functions, and rational functions have places where they don't exist. Generally speaking, that's a vertical asymptote. Sometimes it might be a hole, but let's focus on vertical asymptotes. That is something to consider where the function does not exist, because that's going to help us classify those critical points, right? Because if the function doesn't exist, the derivative won't exist, and that's a big part of, like I said, assessing what the classification of a critical point is. So this is stuff that we want to consider. But we'll get to that as we go over examples of all those different kinds of functions. So for now, what we want to get used to is we could look at this as a fairly strict step-by-step process where we start with a function, and the first thing we're going to do is we're going to determine the derivative. Oops. And then we want to factor, right? Because if we're going to determine where it is equal to 0 and where it does not exist, we want it to be fully simplified, fully factored. That's what we spent so much time on in the previous unit, learning how to simplify fully and what that means. And that's so that we can do this process. So it looks like there's a common factor of 4x, which is nice. And then it factors further. Something to consider as you move forward, and again, we're going to spend a lot of days on this, but something to consider is, sometimes it might not factor, sometimes you might have a numerator or a denominator that doesn't have roots, or maybe it doesn't factor, but it does have roots, so you're using the quadratic formula. All of those things are possibilities, things that might come up. So for critical values, we have them where f prime equals 0 or f prime does not exist. Now, again, when we talk about the type of function we're looking at, not only do we want to consider that the original function is a polynomial, but the derivative of the original function is also a polynomial. So, we've got, it doesn't really matter what form you look at, but I'm looking at that original form. That is definitely a polynomial function, which means f prime exists for all x, right? So that is a required statement. We have to say that somewhere. If it doesn't exist, we're going to talk about where it doesn't exist, but if it does exist everywhere, that is something that's required to say. You have to say that. You have to, you can't just overlook it. It's an important part of our solution, okay? And generally, if it exists everywhere like this one does, I start with that statement because, moving forward, there might be more work to do, but it's easy to just make the statement and then we can move on and we don't have to worry about that anymore. Now, because we've already fully factored the derivative, and you will see when we start getting into curve sketching that I have my own personal sort of step-by-step process of how I go through these solutions. And so that's usually what I do. Not all teachers do that, not all people do that, so it will depend a little bit on how you format your solutions. Obviously, I format it the way that I do because I like it that way, and I think it kind of makes the most sense. It's efficient, it's organized, so I would encourage you to do that when we get into that in the next lesson. But in this case, as I said, because we have the derivative fully factored, we can just state f prime equals 0. We can just state where it's equal to 0. And as you know, I like to do things left to right, so I'm going to take the opportunity to do that now. The first place where it's equal to 0 is -8. The next place is at 0, and the last place is at 2. 0 is an easy one to miss. When we factor out an x, that means we have a solution of 0. Sometimes people miss that, so be careful of that. And now that part's done. So that was sort of the first section of solving a problem like this, is taking the derivative, determining where it does not exist and where it's equal to 0, or, like I said, stating that it exists everywhere. And then we are going to put the rest of the solution into a table when it says classify all points and state all intervals of increase and decrease. This is kind of a funny thing. We're going to get into curve sketching, and we're going to spend a long time on it. And so people get caught up in that, which is great. That's fine. That's what we're going to do. We're going to focus a lot on that. And then on the test, a question like this comes up. It says, state all intervals of increase and decrease. And people say to themselves, I don't understand what that question's asking me to do. I don't know what it means. And so they end up leaving it blank or making something up. What this question, a question like this, is saying is do a first derivative chart, right? So that's what we're going to do next. That's the best way of organizing our information. That's the way I would like you to do it. I suppose you could do it in a different way. It doesn't have to be in a chart, but that's how we do it. So that's how you should be doing it. But that's what you want to know, is that a question like this that's worded this way, what it means is do a derivative chart. And what's a little bit different in this example or this lesson from the first lesson of this unit, when we had domain, a restricted domain, we have to, as I said, we have to talk about all values of x. So we're going to find the first location to the left where the derivative is equal to 0 or does not exist. In this case, it's equal to 0. And we're going to consider less than that location. Then we're going to consider at that location, what's going to happen. And then between that value and the next value, and these are left to right, definitely in order, including all the values that do not exist and where the derivative is equal to 0. So at 0, between 0 and 2, at 2, and that's the last one. So then we're going to consider all values greater than 2. And so this is how we set up our chart, just like that. It'll be a little bit up to you how you choose to fill it in from here. You might choose to fill these spots in. So these were all the places where it was equal to 0, which means they are all horizontal tangent lines. That's all we know for now. And then what we're going to do, and this is a process that we're familiar with, we've done this in other courses, is we are going to pick values in these intervals to represent the interval and test them in the derivative to determine if it's positive or negative. And as we know, if the derivative is positive or negative, will tell us whether or not the original function is increasing or decreasing. So you could pick anything less than -8. So let's say -100, right? You know, we often just use -10, but we could go further and do -100. When you do this testing, there will be circumstances where you might not use the fully factored form. There might be other forms that you use, and again, that depends on how you view things, the different sort of properties that you see in these different algebraic forms of the equation of the derivative. So people might do this a little bit differently, but there are sometimes more efficient ways of considering these functions. But in this case, I'm going to use the fully factored version. So when I put -100 in for each of those 3 x's, okay, in the factored form, I'm going to get negative, negative, and negative, right? They're all going to be negative. And so 3 negatives makes a negative. And that means this is decreasing. Now I pick a value between -8 and 0. So let's say -5. So I'll have negative. -5 plus 8 is positive. -5 minus 2 is negative. So I have 2 negatives and a positive, which means this one's positive. So it's increasing. Now it doesn't always flip, but there are ways to know whether or not it's going to flip. There are other properties of functions that we've learned from advanced functions, and just that we know about these things. And if you are confident in your understanding of those properties, of course you can, some people may choose to take shortcuts. I wouldn't recommend it. Generally speaking, the way that we want to approach a question like this is to do the testing. It doesn't take very long. My point is, don't just assume it always flips. It will not always flip from decreasing to increasing. Often that happens. And I think sometimes because it happens so often, people assume it always happens. And, they stop doing the testing, or they stop considering other properties, and you will get caught if you just do it that way. So do the testing, make sure you know that it is decreasing or increasing at all stages. Let's keep going. So I'll pick 1 for the next interval. And if I put 1 in, I get positive, positive, negative. So 1 negative means it's negative, which means the function is decreasing. And then some big value like 10 or 100 will give me all positive values. And so this is positive, so it's increasing. Okay. Now that I have those properties of the function, whether it's increasing or decreasing, now I can use that to classify these critical points. There are different classifications. There are turning points. There are horizontal and vertical twists, and there are cusps. And again, there are other things about these functions that will tell us whether it may or may not be one of those things. And I'll leave that up to you to think through that for yourself and understand. I'm not going to come out with a full list of all the possibilities, because it would be a long list. And I think it's better if you kind of think of it for yourself. But for polynomial functions, for example, we're not going to have a cusp. That just doesn't happen with a polynomial function. That's one example. So we know none of these are cusps, and you can narrow it down in those kinds of circumstances. In fact, you may for yourself, figure out the kinds of functions that have cusps. It's not that complicated. It's not a hidden fact about those functions, and that might be something that you come to be familiar with. So let's take a look here. So for this first one, I am decreasing horizontal tangent line, then increasing. Okay, the derivative exists. It's equal to 0. That is different from the derivative not existing, right? Those, as we talked about in that first lesson, it's so important that we understand the different ways we classify these things. I don't want to take for granted just because it's a polynomial. I want to be thinking about this. And so in this case, the derivative is equal to 0. It's decreasing horizontal tangent line, then increasing. That means we have a turning point, minimum, and I'm going to locate that actual point. The question does say find and classify the critical points, not the critical values. So it wants me to find the actual point. So I'm going to go ahead and do that. I'm just punching. This is also important, something to get used to. People get confused about whether they're subbing into the derivative or subbing into the original function. And down the road, we're going to complicate that even further. So that's something that we really do need to think about. So if I'm finding a point on the function, I'm subbing into the original function. So I'm just going to take -8 and sub it in there, use my calculator, and I get a value of -2036, which maybe seems strange, but that's not unreasonable. Sometimes we get big numbers or decimals or kind of numbers that you might not expect, something like that. So that's required for when it says to find critical points, which generally, on tests and that sort of thing, it's going to ask for the point. So you have to actually locate the point. I suppose if it just said classify the critical values, then you wouldn't have to do that part. The value is when x equals -8. But for curve sketching, again, we're going to need that point. So starting in the next lesson, that's what we're doing. So it's a good idea to get used to that now. Next one, increasing horizontal tangent line, decreasing. Whenever you are stuck, these are good little quick diagrams to do off on the side, scrap piece of paper, something like that. This is a turning point with a max. Okay, and again, I'll find that value. And it turns out to be at 12. And then finally, it's decreasing horizontal tangent line, increasing. So that's, and again, it exists. Like I'm sort of glossing over this, I know, but it is going back to that full chart with all the different possibilities, where we are taking into account whether it exists or not, whether it doesn't exist, whether it's equal to 0, all of that stuff. Okay, and so this is a turning point with a min. And it is at 2 and -36. Okay, and then we're done. So this is where we, if we were doing a full curve sketch, then we would start actually sketching it. We would have done a bunch of other stuff because that's going to go back to MHF when we do all the other properties that we did before, asymptotes, intercepts, all of that stuff. But this isn't a curve sketch. It's just a derivative chart because it said find and classify all critical points, state the intervals of increase and decrease. So we've done that, right? And we've done it in a nice organized way. And this is how we do it, by considering the derivative and using the derivative to determine if we're increasing or decreasing on the different intervals. This is how we've outlined the intervals, and we have classified all those points. Okay, so that one is for a polynomial function. Usually they're fairly straightforward, a little bit easier. So this one's going to be a bit different because this is clearly a rational function. As I said, the process is the same. Doesn't really matter what kind of a function it is. We're going to determine the derivative and go forward from there. Now, obviously, how you determine the derivative is going to depend on what kind of a function it is. Polynomials are usually fairly easy, and other kinds of functions do require a bit more work. So derivative of the top times bottom minus derivative of the bottom you may choose to do this, as we talked about before, in a different order. If you do a little bit of simplifying in your first step, that's fine. I'm going to not be as efficient, I suppose, just to be able to sort of, color code and highlight what part is the derivative times 1. So we don't need to, again, we don't need to write that, but that's there. Over the bottom squared. And it goes without saying, in the last unit, it said things like, simplify fully or not simplify fully, but when you have to determine where the derivative is equal to 0 or where it does not exist, you have to simplify fully. So we don't have to be told that. We know that we have to do that. Again, you can take a step to sort of collect like terms, or simplify the monomials, or clean this up a little bit if that's how you choose to do it. As you practice and you get more familiar with how these things work out, you might just be able to start factoring out before doing that simplifying. So I can see that there's a common factor of 2 in each of these terms. I'm looking at 2 terms, this one and this one. They're not really terms, but you know what I mean. And I see an x in both of them, so I can factor that out. Whoops. And I can definitely factor out an x plus 4. Okay. And what am I left with? I'm left with, I factored out 1x plus 4, but I had 2, so I'm left with an x plus 4. And I factored out the 2, that x plus 4, that 1 is obviously irrelevant. And I factored out one of those x's, so I've got 1 left. Oh, but it's minus, whoops. So those x's subtract to 0. And this ends up being just 4. So again, I'm, over x plus 4 squared. So this is I'm gonna take this 4, multiply it out front, and I get 8x, and I am going to divide one of those out with one of those, or divide the x plus 4 on top with one of the x plus 4s on bottom. Oops, sorry, that should be to the 4th because I squared it. That looks better. X plus 4 all cubed. And again, as you practice these and get more familiar with them, there are patterns that you can sort of notice that will help you make sure that you're on the right track, that sort of thing. This one cleaned up nicely. They don't always. But you want to factor it as much as you can, clean it up as much as you can. It's going to make your life easier moving forward. And I suppose, technically speaking, if you didn't have it fully factored, but you were still able to do the rest of the question by solving, I'm not going to get into that in too much depth, but that you would probably get full marks for that, because the question doesn't say simplify fully. So if for whatever reason you didn't have it fully factored, but as I say, you solved the rest properly, you'd probably get away with it. But cleaning it up at this point is what I like to do. And, it makes your life easier moving forward because you can focus on the things that you want to focus on. Oh, the other thing I wanted to say, going back to, talking about exactly how you do the factoring and do the derivative and that kind of thing. Your steps might look a little bit different from my steps or somebody else's steps. And sometimes it can be hard to follow. So if you're looking at the solutions and it looks like something magic happened, it's probably just something like this 4 went out front, right, to become the 8. That can be something that when you're looking at somebody else's work, it's not always obvious exactly how that happened. Hopefully you may have done it a slightly different way with slightly different steps, but you got to the same place in the end, and that's fine. If you can't follow the solutions, then it's always good to ask, but that is something to be aware of, that sometimes even just cleaning up little things, even teachers at this point in calculus, in our solutions, we skip a step, as they say, here or there. And it can make it harder to follow. And actually, that's a great lesson for thinking about why we don't want to skip steps, generally speaking, because it makes it so much harder. So 4, critical values, we're done, right? We got the derivative done, we've got it cleaned up. For critical values, y prime does not exist. Well, this one, different from the first example, does have a place where it does not exist. This derivative does not exist at -4, where the denominator is equal to 0. Again, these are rules that you can very clearly and strictly outline for yourself. You're setting the top equal to 0, you're setting the bottom equal to 0, right? So the derivative does not exist when the bottom is equal to 0, as long as it's fully simplified. So that's at x equals -4. However, again, going back to all of the properties, all the stuff we know about different kinds of functions, this is a rational function, and it would have a vertical asymptote at -4. We already know that. So when I write this out, and you are required to write that out for a full proper solution, I'm just going to say, but we're not worried about that location because it's a vertical asymptote. So it's not a critical point because it's not a critical point that we have to classify. You'll see when we do the chart that we will include that point, but it's a vertical asymptote. We already know that, so we don't need to worry about it any further. Okay, and then y prime equals 0, just at x equals 0, where the top is equal to 0, right? If for whatever reason you don't have it cleaned up, you can always just set the top equal to 0 and solve it. In this case, I don't think you would ever really do that, but there are other cases where you might. You may actually look at it and be like, there's something weird about this one, and you can always set it equal to 0 and solve, just like we did all that solving in MHF, how to solve all different kinds of functions, right? So that's always something that you can fall back on. So now that we have these locations, we are going to set up our chart. And we do include vertical asymptotes. We talked about this before. We do include vertical asymptotes in this chart. It is important because it is a place where a function can change from increasing to decreasing. So even though we know it's not going to be a local max or min, it is relevant to talking about intervals of increase and decrease. So we're going to do x less than -4. We're going to talk about at -4, between -4 and 0, at 0, and greater than 0. Okay, so at -4 it does not exist, and we already know that's a vertical asymptote. Right? If it does not exist, but there's other stuff going on, it's a different kind of function, that doesn't necessarily mean it's a vertical asymptote. We know it's a vertical asymptote because we know something about the original function. And at 0, I know that the derivative is equal to 0, so it's a horizontal tangent line, but so far that's all we know. Now I take something in the interval less than -4, so let's say -10, sub it in. -10 on top gives me a negative. -10 on bottom is going to give me a negative inside the brackets. And when I cube that, it remains negative, right? So I've got negative on top and bottom, so that is positive. Therefore, the original function is increasing. Pick something between -4 and 0. So let's say -2. Sub it in, I get a negative on top, but I get positive on bottom, so it's negative. If you aren't sure how I'm coming up with whether the derivative is positive or negative, if I'm going too fast or you're missing that, go back and look at it in a previous lesson, because we've talked a lot about this interval testing, both in MHF and previously in this course, or ask. Okay, I can go over it more slowly, but I'm kind of assuming that people are able to do this testing at this point on their own, and they can follow what I'm doing. So now finally pick an interval in that's greater than 0. So let's say 10, sub 10 in for x on top. 8 times 10 is 80, which is positive. I don't care what the actual value is. I just care that it's positive, and sub 10 in to x in the bottom there. And again, I get positive. So positive over positive, whoops, is positive. So increasing. So again, this one I'm not worried about. It's a vertical asymptote. That's done. But this other one is a turning point because it changed from negative to positive and the derivative was equal to 0. So that's how I know it's a turning point. Is it a max or min? It's decreasing, 0, increasing. So it's a min. And subbing into, again, the original equation to find that actual point. That's actually the origin, 0, 0. And again, now we're done. Okay, we've got a couple more left to do. Now these ones are quite different. We looked at polynomial type function. We looked at rational type functions. These ones are different. These are not functions that we really explore at all in MHF. So if this feels new, that's okay. We have done derivatives of these kinds of functions before. Subtract, make sure that you do the fraction math right. If you have to use your calculator, use your calculator. 5/3 minus 3/3 is 2/3. Now from here, there are two ways of doing this, and you want to pick the way that you are most comfortable with and just use that method moving forward. You know, if you're comfortable with both, then that's fine, and you may choose in some cases to do it one way and in some cases to do it the other way. I would say generally people pick one way and do it that way. They're about the same amount of writing, they're about the same amount of efficiency, they're just kind of different ways of doing things. So the way that I like to do it, because it's just what I've gotten used to, is by common factoring out. But some people don't quite see how this common factor works because of the exponent laws that are required, the manipulating the exponents. And if you feel that way, then you can do it the other way. It's not really a time saver or anything like that. So I can see that I can factor out a 5/3. And then really what you're always doing is you're factoring out the smallest. So I'm just going to factor out x to the negative 2/3. I don't really have to think about it. I don't really have to worry about it. I just know that I'm going to factor out the smallest exponent. Here's the hard part. What do I get in this first term when I factor out x to the negative 2/3? Well, we're dividing, so it's x to the 2/3 divided by x to the negative 2/3. What do you do when you divide powers with the same base? You subtract the exponents, so this ends up being 2/3 minus negative 2/3, which is x to the 4/3. And that's the part that if you don't see that or don't quite get that, then that's fine. You can do it the other way. But if you do get it, this might be a way that you like and that works for you. And we'll notice that in the second term, I actually factored out the entire thing. This doesn't always happen. It's not always going to be 1. It might be something else. Usually it is something simple. It's not usually something complex. Like it might be 4, it might be 5, it might be 20, 10, whatever. But not always, okay? And then I need to just take care of the negative exponent. So I'm going to do 5 x to the 4/3 minus 1/3 x to the 2/3. Right? So now that is fully cleaned up. The other way that we can do it is by getting a common denominator. So I have 5 x to the 2/3/3 minus 5/3 x to the 2/3. Now you don't have to rewrite this necessarily, as long as you can see it for what it is. So rewriting it like this is going to help us see it as fractions for the first time that we're doing it. But if you don't have to rewrite it, you might be able to skip that step kind of thing. And what we're going to do is multiply this one by x to the 2/3 over x to the 2/3 to get a common denominator. So on top, 5, x to the 2/3 times x to the 2/3. Again, I'm adding the exponents, so I get x to the 4/3. And on the bottom, I get a common denominator of 3x to the 2/3. Then I'm going to factor a 5 out of the top. And notice that we get the exact same thing. And it's in basically the same number of steps, depending on how you see it, on how you how comfortable you are with exponent laws and with factoring, that kind of thing. Like I said in the beginning, it's not really a big deal if you do it one way or the other. They're both about the same amount of work. All right, now that we've got that done, taken the derivative and fully cleaned it up, whatever method you do, it's gonna be the same steps moving forward. So it does not exist at x equals 0. Now this is really important. Compare this to the last one. This is where a lot of learning can take place. If I compare this to the last one, because I think this is going to be something that if you don't take the time to make this connection, then you're going to be kind of lost and feel like or question, well, I don't understand why in this case it's this and in this case it's this, and how I tell the difference. In the last example, we had a place where the derivative didn't exist, but the function also didn't exist. We already knew that the function had a vertical asymptote at that location. That's not true in this case. There's no reason to believe that this function has a vertical asymptote. A vertical asymptote occurs when the denominator is equal to 0. This doesn't have a denominator. Yes, it has some strange exponents, but none of them are negative. There's no denominator there, right? So this kind of a function does not have a vertical asymptote. That's something that you have to, come to terms with, be able to understand. But the derivative doesn't exist. So that is telling us something. That goes back to that chart that we made in lesson number 1 of this unit, where we are outlining the different situations that allow us to classify these critical points. So that's going to come back to that idea later when we get to this. Okay, so that is an important connection to make, that the derivative does not exist, but the function does, right? And different from the last example. F prime is equal to 0 when x to the 4 over 3 minus 1 equals 0. Now this might be something that you can do quickly. You may not have to do this in several steps. I'm going to do it nice and slow because this is something that's a little bit new and you might not have really seen it before. And I think if I just kind of glossed over this, then people would maybe be a bit confused by it. And this is what I said in the last example. You can always just take whatever it is, the numerator or denominator, and set it equal to 0 and start solving. So what I'm going to do solve is I'm going to move the 1 over. Now I'm going to cube both sides. You do not have to do this in separate steps. That is taking care of that denominator in the exponent, right? You don't have to do these in separate steps, but I'm just, again, showing to make sure that everybody understands how we're getting to that final step. Now I'm going to take the 4th root. 1 cubed is 1. And this is something that we don't see a lot of. We see it a little bit in MHF, but we don't see it a lot. And we see square roots of things a lot, starting in grade 10, even in grade 9, but we don't see it with other higher exponents. But when I take the 4th root of something, it's just like a square root where I have to have the plus minus, right? So I've actually got 2 values here. And so you do not have to include those steps, but you need to make sure that you understand that there are two values where the derivative is equal to 0, positive 1 and negative 1. And again, this is a trick to fall back on. You can always just take the entire numerator or denominator and set it equal to 0 and solve. So we're starting at negative 1 on the left. Our next value is 0. Our next value is 1. And there we go. And we will have a few times where we have a lot of intervals. So the last couple of examples didn't have too many. They each had 2 maybe, or did the first one have 3? But there will be cases where we might have even more than that. So just be aware that it can happen where you have a lot of intervals and you have a long table. Okay, so at negative 1 it was 0. At 0 it does not exist. At 1 it is 0. So these are horizontal tangent lines. Horizontal tangent line. And this is the difference. This is not a vertical asymptote. The derivative does not exist, but the function did exist. So this is a vertical tangent line. And again, this goes back to that table that we made at the beginning, where we can classify all the different kinds of critical points or critical values. Okay, and again, I'm going to whip through this, but I'm picking values in these intervals to represent them. So, I'd start with negative 10. This one's going to be a bit tricky. I'll have to pick negative 0.5 and positive 0.5. But again, you can use your calculator to do that. We will talk about that moving forward. Or if you can do it in your head, if the factored form is nice. In this case, the factored form isn't that nice. So you might use your calculator to actually test these. And if you have to program your calculator with the function, you can save a lot of time. But I'm not going to get into that right now. We'll talk about that. You can ask about it, or we'll talk about that at a later date. So we get positive for this one, negative for this one. This one, again, is negative. And this is what I said before. It doesn't always flip back and forth. So you can't just assume that it does. And then that one's positive. So this is increasing, decreasing, decreasing, increasing. And if it's going from increasing to decreasing, we have a turning point max. And if it's going from decreasing to increasing, we have a turning point min. Okay, and these points subbing into the original function are negative 1, 4, and 1, negative 4. And this one is a bit different. What happens if it's decreasing before and it has a vertical tangent line and decreasing after? Well, it's decreasing, then it's vertical, and then it's still decreasing. Remember, this is what we talked about before. Otherwise, it would be decreasing vertical and then increasing, which would be a cusp. So again, we can sort the different circumstances into all of the different possibilities that we have, like a vertical tangent line, a vertical twist, or a cusp, by looking at whether it's decreasing, whether it's switching from decreasing to increasing or increasing to decreasing, or it's not. So in this case, we're not switching. So this is a vertical tangent line that is a vertical twist, and it happens to be at 0, 0. So again, I have determined all of the intervals of increase and decrease and classified the critical points because I found the points and I've classified them into those categories that we discussed before. Okay, we've got one more. If you want to go ahead and pause the video and try to take the derivative of this on your own and clean it up, that's a great idea. Again, that's going to be the first step. We can see that this is not a polynomial, it's not rational, it doesn't have a denominator, so those are all things that we're thinking about. It's similar to the third example that we just did, but it's going to have a little bit of a difference. So we'll take the derivative and go from there. All right, so here we go. When I multiply by 2/3, the 3's divide to 1, right? So I get negative 2 subtracting 1 from 2/3 is negative 1/3. Again, this doesn't always happen that you have the same coefficient in each. We're setting up these questions to work out this way. So in math class, sometimes that happens. They're not always the same. Sometimes, often you'll probably see that they do factor. They're not always equal. But, that's not a rule. That's just how it's been designed. So that won't always happen. So again, I'm going to factor out a 2, and I'm going to factor out the x to the negative 1/3. Whoops. The smallest exponent. When I divide x by x to the negative 1/3, I'm subtracting the exponents. 1 minus negative 1/3 is 1 plus 1/3. So I end up with x to the 4/3 again. Again, it's not always 4/3. That's just, both of these worked out that way, but it doesn't always work out that way. And I factored out the entire second term, so I get that. And then finally rewriting, 2 x to the 4/3 minus 1 over the cube root of x. Okay. Critical value. So you can do it the other way. You can do a common denominator if you like. I'm not going to show both ways every time. Again, this has a place where the derivative does not exist, but the function did exist at 0. If you're not sure, what could you do to see if the original function does exist? Because that's something you have to do. To classify, you have to know if the function exists there. You could just sub 0 in and see what you get, right? If you get an error on your calculator, then it's probably undefined. It's probably a vertical asymptote. If you get a value, that means the function exists. So this is similar to the third example where the derivative does not exist, but the function does. And the top is very similar to the last one we had, so I'm not going to show all those steps, but we get plus or minus 1 again. Okay, so x less than negative 1. In fact, this table is going to look almost identical or identical to the last one. I don't know if it's exactly the same. I think it is. Okay, and it's 0, does not exist, 0. That means a horizontal tangent line. Again, we have a vertical tangent line. We know that because the function exists, but the derivative does not. So that's a vertical tangent line, and then a horizontal tangent line. And then again, picking values and subbing into the derivative to do this testing, I get negative, positive, negative, positive. So that part is not the same as the last one. This is decreasing, increasing, decreasing, increasing. Horizontal tangent line that is changing from decreasing to increasing is a turning point, min. Again, you'll notice that I'm kind of skipping over these things. We've talked a fair bit about it. Decreasing, horizontal, increasing, that's a min. You can draw that every time if you like, off to the side or whatever you need to do. Hopefully, I'm not going too fast over that. Same thing here. This is a turning point. It's going from decreasing to increasing, so it's a min again. And as I said before, I'm subbing these x values into the original equation to find the actual point. And the last one that we want to focus on here that is a bit different is I'm increasing and then vertical tangent line and then decreasing. That's the only way to draw that. That is a cusp, right? And at this point, and it's cusp with a max. And again, I know that just because I just draw it, right? I just drew it. So I know what that looks like. I can visualize it. If you have questions about how do you know that's a cusp, well, then you might need to go back and rewatch parts of lesson 1 or ask and we can go over it. But it just has to do with whether it's increasing, decreasing before and after the value, and whether it's equal to, the derivative is equal to 0 or does not exist, and then also whether the original function exists or not. That's how we narrow down all of the different situations that you can have. So that's all there is to it. I mean, I can explain it again. We can go over it again, but the lesson number 1, where we talk about all the sort of 6 different situations, that's where we go into detail on why they are. So if you're really unsure, I would recommend going back and watching that again, or watching parts of it, obviously. Or you can ask and we'll talk about it again. But there's no magic here. It is just sort of a series of rules. And then again, I sub this in and I get 0, 0. And that's that. So we saw polynomial function, rational function. We saw 2 other kinds of functions, and once we start sketching these functions, they're very different from the ones that we sketch in MHF, so it's kind of new, that they're interesting. It's neat that we can start to understand more about different kinds of functions and start to visualize these different functions. But we saw 2 examples of functions that have vertical twists or cusps, those kinds of things that are different, like I said, from the other functions that we've seen in the past. So we are going to sketch some of these. And when we sketch, that will help us really visualize, because we'll actually have to draw it out, and that will help us put the pieces together as well. So if you're not, so go through the steps, make sure that you're able to take the derivative and clean it up. Make sure that you understand how the table works. But if you're having a bit of a hard time classifying, as I said, I would go back and rewatch part of lesson 1, or when we move on to sketching, now it's going to be a couple of days before we get into some of the more complex sketches, but when we get to those, it should help clarify why we're classifying these things the way they are. Okay, but that is intervals of increase and decrease in classifying critical points.